So, in this session we are going to discuss about the stepwise procedure for the design of shell and tube heat exchanger. This procedure was originally outlined by Kahn, and there are other definitely more advanced this shell and tube or heat in general heat exchanger design procedure, just like epsilon NTU method proposed by London and Kay, but that we are not going to discuss now. Some of the leftover topics throughout the entire syllabus, like just like this epsilon NTU method and some of the others leftover topics of different other subjects will be discussed later, right. So, here we are going to discuss the method of Kahn as the classical shell and tube heat exchanger design technique. So, what is a stepwise procedure that I am going to simply briefly explain. So, design of shell and tube heat exchangers. So, algorithm. See, we will start with energy balance, right. Generally, the mass flow rate of the individual stream, the hot stream and the cold stream will be given, the hot stream cold stream inlet will be given, and one of the target mostly the hot stream temperature, outlet target temperature will be given. So, based on that we can write that perform energy balance to calculate the heat duty and unknown temperature if any. Now, in real life what happens? In real design procedure, you see that cold stream inlet and target outlet will be precipitate and nothing else will be given, its mass flow rate will be given. So, here see from this process plant this data, we know that temperature of that circulating cold water, that is inlet temperature, right. And the outlet temperature we consider to be same as that of the inlet to the respective plant's cooling tower data. The respective water inlet temperature of the cooling tower, that must be the outlet temperature of all heat loads. So, from there we can get this inlet and outlet temperature. So, once inlet and outlet temperature of the cold stream, that is specifically water if I am using, the utility water if I am using, if that is known, we can calculate the mass flow rate. So, overall it may be a temperature calculation, unknown temperature calculation, or it may be a mass flow rate calculation. So, whatever it is, once we finish that, we can actually calculate what is the heat duty required. So, once the heat duty we have fixed, right. Next, calculate LMTD upon determining the number of passes and also evaluate FT, the LMTD correction factor from R and tau, right. Third step, see, in order to calculate the area, we have to know the heat transfer coefficient, overall heat transfer coefficient, but we do not know overall heat transfer coefficient. So, we have to assume. So, obviously assumption means it must be a kind of iterative technique. Assume UD based on outside area, right. And if you follow the book of Kant, there is a range of UD given for different types of combinations like organic, like shell and tube both are organic fluids. So, organic combination, gas organic combination, next inorganic combination, etc. From there, so we can get a range and we can assume some mu d, and based on the outside area we will calculate that, or we will actually determine that. Assume mu d based on outside area and calculate A, that is the heat transfer area required as Q is equal to U d into A into Ft into LMTD, right. So, we will get A. Next, we have to regenerate the value of UD. So, what should be the procedure? First, fix the tubes or tube dimension. First, okay, this is first you fix the tube dimension. That is DO, DI and L, the tube lengths, right. So, evaluate the number of tubes as n equal to A into this pi into D naught into L, and also the number of tubes per pass as this small n equal to capital N divided by P, the number of tube passes. Okay. So, tubes, number of tubes has been calculated, and as we have assumed the number of passes, we have also calculated the number of tubes per pass. Based on n, the total number of tubes, fix the diameter of the shell. Assuming or considering tube pitch PT and tube layout, right. So, there are tables in the book of Kant or also in standard other heat transfer books by which we can actually calculate or you can fix the shell diameter based on the number of tubes, this tube pitch you are using, and the this tube layout, that whether it is a square pitch or a triangular pitch. So, shell diameter, tube pitch has been fixed. Select the type of baffles commonly use 25% segment cut, 25% cut segmental baffle. So, select the type of baffles, baffle spacing B and baffle spacing maybe, right. Because why this is necessary? As we have seen the formula of Kant for HO, we know that B, PT, these values are necessary to calculate the HO. So, once we have fixed the shell diameter, we have fixed the number of tubes, we have fixed baffle spacing and the tube pitch. Now, using or next calculate HI and HO using appropriate equations or JH versus RE chart. So, you have got HI and HO. Determine this clean overall heat transfer coefficient UC as 1 divided by HI based on outside diameter UCO. So, HO plus 1 by HI, this DO by DI, right, plus this delta X divided by K into this DO by D bar L. If you include this thickness, where this delta X is equal to DO minus DI by 2. So, we have included the metal wall resistance outside and inside. So, this K is a case for tube material, right. Next, select RDO based on the type of fluids, type of liquids, or rather type of fluids, and calculate UDO as, or rather 1 divided by UDO is equal to 1 by UCO plus RDO. Right. Evaluate heat transfer area as A is equal to Q divided by this UDO, the new UDO, right, this to be used here, into FT into LMTD. Right. If the area, or if the previous area is within or within 10% higher than newly calculated area, proceed for mechanical design, which we are not going to discuss. Right. Otherwise, you have to go for assuming a new UD. Go back to step 3, or rather proceed not for mechanical design, proceed for step 12. Evaluate delta PT and delta PS. This delta PT is a total tube side pressure drop, whereas this delta PS is a respective shell side pressure drop, right. If delta PT and delta PS are within allowable limits, then proceed for mechanical design. else further adjustment this adjustment either in step 2 or in step 4, where you are fixing the tube dimension, is necessary. Right. So that's the stepwise procedure of the design method outlined, shell and tube heat exchanger design method outlined by Carney. So you see that here it's a type of iterative method, and that's why you have to be wise in choosing this UD and also the tube dimension. Here we have to remember that commonly we should try with this 3/4 to 1 inch tube, and if it fails, if the pressure drop is still higher, right, next we have to go for higher this tube diameter, like 1.25 inch or 1.5 inch maximally for this tube diameter. And we will start with this 1-1 exchanger if you don't have any background or baseline experience in designing heat exchanger. So if it fails, then we will go for 1-2, then 2-4, etc. So that's the technique, and there are a lot of these simulation software like HYSYS, Aspen, etc. These commercial packages where we can also perform the shell and tube design. So that's all about heat transfer. Epsilon NTU method will be discussed later when we are going to discuss these leftover topics. So next we are going to solve some gate problems of this subject, right. We'll start with 1 or 2 problems from heat exchanger itself. See, what is the question? Let's consider a new type of arrangement which is similar to square pitch but includes a central tube as shown. See, this square pitch, additionally a central one. So this tube to tube, center to center distance is PT, and the diameter of the tube is D0. That's given. All the tubes are having an outer diameter D0 equal to 2 centimeter, right? Whereas the tube pitch is 3 centimeter. This is 3 centimeter. Hydraulic radius of the shell. So RH, its weighted area by weighted perimeter. Note that hydraulic diameter is, or equivalent diameter is 4 times weighted area by weighted perimeter. So here what is the weighted area? This hatched area. Right. So it's PT square minus. So here for this corner tubes, 1/4, 1/4, 1/4 and 1/4. So 1 tube and additionally a central tube. So minus 2 into pi by 4 D naught square. divided by weighted perimeter. There is a full perimeter for the central tube and 1/4, 1/4, 1/4 and 1/4. That is again another full perimeter. So, it is 2 pi d naught. So, you substitute the values, you can calculate RH in centimeter. Okay. This is the first question. Second question. In a shell and tube heat exchanger, the baffle spacing is increased by 4 times, keeping all the other parameters unchanged. The ratio of new shell side heat transfer coefficient to old one. See, we have already discussed HO from the Carnot's formula is 1 divided by B to the power 0.55, right. So, HO2 by HO1 is equal to B1 by B2 whole to the power 0.55 and B2 is 4 times higher than B1. So, it is 1 by 4 to the power 0.55. So, it is close to 2. Okay. Now, you see third question. In a shell and tube heat exchanger, if the shell length is Ls, shell length it is Ls, baffle spacing is Lb, and baffle thickness Tb. The number of baffles in the shell side, it is simple mensuration, nothing else. See, in the shell, there is the total length, right, and here you may be using NB number of baffles, right. So, how many spacing? 1, 2, 3, 4, 5, 6, right. So, 6 into LB, or rather this, how many baffles we are using? 5. So, N plus 1 into LB. N is the number of baffles, right, plus N into this TB is equal to must be Ls. So, N LB plus TB is equal to Ls minus LB. So, N is equal to Ls minus LB divided by LB plus TB, right. However, there is no such option. What you can say that here, in order to match that option, as LB is much greater than TB, we can write that this is Ls divided by LB plus TB minus 1 approximately, right. In the second term, we are neglecting this TB because this is close to 1. So, that is the answer. Okay. So, next another problem. What is that? A saturated steam, we have saturated steam at 3.32 bar, it's 410 Kelvin given, is fed to the steam chest of the fast effect of a multiple effect evaporator. So, here we have the fast effect. This is the steam chest, and the residual pressure in the condenser attached to the last effect. So, here we will have the last effect, here we have the condenser. So, here the pressure is 0.195 bar, respective boiling point is 333 Kelvin. If the sum of boiling point elevation, sum of BPEI, which is say BPE total, it's 41 Kelvin. Right. Determine the number of effects to be used. Available temperature driving force in any effect. So, delta Ti should be at least 8 Kelvin. So, it is pretty simple. You see, the overall temperature difference, delta T overall, is 410 minus this 333, right, minus boiling point elevation, 41. So, number of effects we can write, that is 410 minus 333 minus 41 divided by 8. So, from it is very simple. So, you have to understand what this equidistribution of temperature means, and from there we can calculate this number of effects. Right. Second, another question. An aqueous solution of high molecular weight. High molecular weight means what? What is the implication? Boiling point elevation is negligible. High molecular weight solute is concentrated from ZF is equal to 2% to X is equal to 35% by weight at a rate of feed flow rate is 6000 kg per hour. Right. The dilute feed at, so TF is 50 degrees Celsius, enters the first effect, saturated steam, P steam is 2 bar and T steam is 120 degrees Celsius. Is supplied to the first effect while the pressure of 0.019139 bar is maintained in the last effect. So, Pn in the last effect 0139 bar, right. Corresponding temperature Tn is 12 degree. The overall heat transfer coefficient in the first and second effects, that U1 equal to 2000 watt per meter square Kelvin and U2 equal to 1000 watt per meter square Kelvin. The driving force is the second effect. So, we have to calculate delta T2. See, from the equidistribution of heat load, we know that delta Ti by delta T overall equal to 1 by Ui by summation of 1 by Ui, right. So, delta T overall will be what? There is no molecular weight difference, there are more high molecular weight, so no boiling point elevation. So, we have the T steam 120 and Tn 12 degree. So, del T overall is 120 minus 12, that is 108 degree, right. And we do not need anything else except this U1 and U2. So, U1 and U2 that we have to substitute, rest of the data are all excess data, right. We do not have to consider them at all. So, another problem on evaporator, it is 2004 gate problem. It is desired to concentrate a 20% salt solution. So, ZF is 0.2, directly let us write in mole fraction or mass fraction, to X equal to 0.3 in an evaporator. Consider a feed flow rate of 300 kg per minute at Tf equal to 30 degrees Celsius. The boiling point of the solution Ts is 110 degree and the latent heat of vaporization is 2100 kilojoule per kg. Specific heat of the feed is 4 kilojoule per kg Kelvin. The rate at which heat has to be supplied in kilojoule per minute, Q dot in kilojoule per minute, how much it is, right. So, you see that feed flow rate is given. So, we know that Q dot is equal to F Cpf Ts minus Tf plus V into lambda s. Now, you have to calculate V, and V, what will be that? F minus L, and what will be L? L is equal to FZF minus divided by X, right. So, this Q dot F 300 kg per minute, always write the unit, Cpf, it is 4 kilojoule per kg Kelvin into Ts minus Tf, 110 minus 30, so it is 80 degree, 80 Kelvin or 80 Celsius, right, plus V should be in kg per minute into this lambda is 2100, right. Now, L is equal to F, that is 300 into ZF, that is 0.3 divided by, sorry, ZF is 0.2 and divided by 0.3. So, you can calculate it to be 200 kg per minute. So, V is equal to 100 kg per minute, right. So, here we have to substitute 100 and we can calculate the answer in kilojoule per minute. So, that is typical energy balance and coupled with material balance problem. So, just like I am not going to solve it, like a problem of 1 mark, 2 marks, the overall heat transfer coefficient for a shell and tube heat exchanger for clean surfaces is 400 watt per meter square Kelvin. The fouling factor after 1 year of operation is found to be HD naught. Previously it was U naught, that is UC naught, is 2000 watt per meter square Kelvin. The overall heat transfer coefficient at this time. So, what we have to do, as the no tube data is given, we can simply write 1 by UD is equal to 1 by UO, UC naught, or basically 400 plus 1 by or plus this 1 by HDO, right. The fouling factor is given in heat transfer coefficient unit, not in resistance unit. So, that is to be taken care of. Just see 2019 2 marks problem. A solid sphere of radius, solid sphere of radius 1 centimeter, initial temperature 25 degrees Celsius, exposed to a gas stream of 100 degrees Celsius. For the solid sphere, the density is 10 to the power 4 kg per meter cube. Its specific heat capacity Cp or Cps 500 joule per kg per Kelvin. The density of the gas rho infinity is 0.6 kg per meter cube, right? And the solid sphere and its specific heat capacity Cp infinity is 10 to the power 3 joule per kg Kelvin. The solid sphere is approximated as a lumped system and specific heats are constant. If H between the sphere and the gas, so H is 50 watt per meter square Kelvin. Then the time needed for the sphere to reach 95 degree. So Tf 95 degree. Sorry. Tf to 95 degree. What is the time? So you see this it's simple balance equation. So H is given. So you can solve it as minus of m sphere. M sphere is this 4/3 pi Rs cube into rho s into Cps into dTs dt, right? And that's equal to H into 4 pi Rs square into the temperature difference, which is Ts, let's say right small Ts, because they are not absolute temperature, Ts minus T infinity, right? Heat transfer coefficient is given, so from there we can directly solve. So if I do that, a bit of simplification, so you see 4 pi r square, 4 pi r square, right? So minus of dTs dt is equal to 3h divided by Rs into rho s Cps into Ts minus T infinity. So it will be that log of, so dTs divided by Ts minus T infinity. So log of this Ts I minus T infinity divided by Ts minus T infinity, right, equal to exponential of this 3h divided by Rs rho s Cps into T. So this minus and this plus will cancel out. So whether it is correct? No, I think this will be TSI. Yes. So we can get here this Ts minus T infinity to the denominator and log of x. So it's just like that. Yes. Right? So there will be a minus sign. Yeah, because we are integrating from TSI to TS, so there will be a minus sign. So that will be the result. Yes. See another question. Vapor bubbles are formed in a nucleate boiling regime. Vapor bubbles are formed in a nucleate boiling regime at a frequency 10 bubbles per second per nucleation site, per site. There are 100 nucleation site 100, right, and there are 100 nucleation site 100 per meter square of heating surface. The latent heat of vaporization and density of the vapor under operating condition are 1000 kilojoule per kg and 1 kg per meter cube. The diameter of the bubble dV 10 to the power minus 3 meter. Assuming that the entire heat is supplied is used up for vapor generation, the heat flux Q in watt per meter square. Right. So, you see that what is the total mass of the bubble, or mass flow rate of the bubble. So, its frequency multiplied by number of sites per meter cube per meter square into this volume 4/3 pi rs cube, right, or rather pi by 6 dB cube into rho s, that is the mass, and the q dot will be that multiplied by lambda s. So, that is my answer. So, substitute the values, you will get the answer. Okay. So, that is the question of vapor bubble, but we do not have to use any understanding of this nucleate boiling and all. It is pretty simple. See another type of question. Water enters a thin walled tube. We have a tube, length 1 meter, diameter 3 millimeter, at an inlet temperature of 97 degrees Celsius. Mass flow rate 0.015 kg per second. Right. The tube wall is maintained at 27 degrees Celsius. The given data for water, the density has been given, viscosity given, I am not writing it, specific heat given, right, inside heat transfer coefficient HI is also given. We have to calculate this, say TI, T inlet, and TO we have to calculate. So, you see there will be heat loss, and we can write m dot into Cp into this 97 minus, or rather we write in symbol Ti minus To, right. So, m dot is given, Cp given, Ti minus To, that is basically q dot, and we know that is equal to this H into this area, that is pi into capital D into L, right. into LMTD because the temperature is progressively changing. So, LMTD expression will be Ti minus, let us say the surface temperature is Ts, Ti minus Ts minus this To minus Ts divided by ln of Ti minus Ts divided by To minus Ts. So, here it is going to give you Ti minus To, right. So, the numerator and this cancels out, and ln of Ti minus Ts divided by To minus Ts equal to this pi d LH divided by m dot Cp. So, from there using this exponential relationship you can calculate this Tu, right. So, that is all about heat transfer. In the next session we will start thermodynamics. Thank you.